Welcome back, folks. And the video for today is going to focus on valence shell electron pair repulsion theory, otherwise known as VSEPR. Alright, so the purpose of this is we're going to apply this theory to help us to determine the geometry or the shape of a covalent molecule in three-dimensional space. Okay, so far we've talked about Lewis structures, but when we talk about Lewis structures, we're confined to the two planes of the board or the paper. We want to actually see what the shape or geometry of the molecule would look like if we were actually to allow it to expand out into three-dimensional space. So this theory helps us to go from a Lewis structure into that third dimension. All right, so what drives this is the assumption that the electron pairs that surround the central atom are going to repel one another. It makes sense that electron pairs, when they interact, ought to repel. Okay, so if that happens, then the goal is going to be to get those electron pairs that happen to surround the central atom as far apart in three-dimensional space as we possibly can. And when we do this, the resulting shape is going to define the geometry of that molecule, again, in three-dimensional space. So it's actually pretty easy to do when you start thinking about it. All right, so we have five basic cases that we're going to talk about. Then in class, we're going to see that these cases have various subsets associated with them as well. But it's always good to start with the basic situations. All right, so what I like to do is I classify the cases as this: AX2, AX3, AX4, AX5, and AX6. Now in all of these cases, the A is going to represent the central atom in our Lewis structure. The X is going to represent some other atom on the outside. And of course, we're going to have bonds between those atoms. All right? So if I look at AX2, for example, I could represent this quite simply as an A in the middle, and then I could put an X on either side of it. So again, what I'm trying to remember here is that I want to get those electron pairs that form the bonds as far apart or as away from each other as I possibly can. So the best way to do that is to put a bond on one side of the A and put a bond on the other side of the A. All right? Now I'm leaving out, of course, any non-bonding electrons that might actually be on the outside atoms. All right, so in a situation like this, the best thing we can possibly do is we can get those things on opposite sides of the central atom, and we can define now a bond angle by doing that. Now if I define a bond angle by doing that, that angle is going to turn out to be 180 degrees. That's the best I can possibly do. So we can actually assign a name to this geometry. It forms a straight line, so we'll call it a linear geometry. All right? And we'll come back in class and take a look at examples, real-world examples of these as well. All right, so the next thing we might have is an AX3. So let's think geometrically. How's the best way that I can get three electron pairs around a central atom? Okay, so if I think about it, probably the best thing I can do is to take my unit circle and divide by 3. So if I do that, I'm going to get an X up here, I'm going to get an X here, and I'm going to get an X down here. Now if I do that, dividing my 360 degrees in the unit circle by 3, I get 120 degrees. So my bond angles now are all the way around the circle are going to be equivalent at 120 degrees. Okay? That's the best way I can get those three electron pairs away from each other in three-dimensional space. All right? Now, I have a name for this because if you think about this, put this thing in a plane, what are you going to get? If I kind of connect the dots here, you're going to get a triangle. You're going to get a triangle. So we have a name for this geometry. We call it trigonal planar. So that's the best I can do with three pairs of electrons around the central atom. Now what about AX4? Now, if you look at AX4, you might say, okay, following along with what we just did, maybe the best thing that we could do would be to look at a situation like this, where I can sort of space the X's out on my plane like this. And if I do that, make my bonds, what are my bond angles all the way around in this case? Well, again, now what I'm doing is I'm dividing my unit square by 4. And if I do that, I end up with 90-degree bond angles. Okay? Now, would you believe me if I told you we could do better than that? Because what we're forgetting at this point is that we can actually expand out into 3-dimensional space. And if I do that, I can actually open up these bond angles a little bit larger than 90 degrees. So watch this. I'm going to redraw this accordingly. All right? And the best way to actually show this is kind of like a pyramid with something on top of it. So I'll put an X there. This wedge actually represents something kind of coming out of the board at an angle like this. So I'll put an X there. Then I can have a wedge that goes back. That represents something moving back into the plane of the board. Like that. And then finally I can have the third leg of the pyramid, which would be here. Okay? So again, think of this as like a pyramid with a triangle as its base, like a tripod, for example, with something extending out on top of it. Now, if we actually pop into 3-dimensional space like that, what we can do is open up these bond angles a little bit further. So now, rather than being at 90 degrees, I actually get bond angles of 109.5 degrees. And that's preferential over the 90-degree option. Okay, so this is not the way we want to go. We want to expand out into 3-dimensional space. We want to make a tripod with a stick off the top of it. Okay, and we have a name for this. We call this a tetrahedral geometry. It's called a tetrahedral geometry. Now, we have 2 other options here as well. We've got AX5, okay? And for the AX5, again, I have to think about being in 3-dimensional space because now I'm going to add another pair of electrons in. So here's how we do it. Put my A here. And now what I'm going to do is I'm going to essentially, looking down on this thing, make a plane with a triangle in it. Okay, so I can kind of show an X coming out here. I could have an X going back in like this and an X coming out like this. So this is a triangle if I'm looking straight down on it. And then I can have an X down here, and I can have an X up here. Okay? So if I look at this particular geometry, what we're going to notice is that we're going to have 2 different kinds of bond angles here associated with this one. Okay? I'm going to have bond angles that kind of go around the plane here. So I have the bond angle that goes from here to here, and then continues from here to here, and then back around from there to there. Now, if we're looking straight down on that as a triangle, that bond angle is going to be, again, 120 degrees. Okay, so those bond angles turn out to be 120 degrees. Now, I also have the bond angles that happen between here and here. It's also included the bond angle that I get between here and there. Now, if you look at that bond angle, that's a 90-degree bond angle. All right, so with the AX5, we actually end up getting 2 different bond angles. We get what are called the axial bond angles. Those are the 90-degree ones because they travel up and down. And we get the equatorial ones, which are the 120-degree ones because they go around the equator. All right? So what would we actually call that particular geometry? As it turns out, we call it a trigonal bipyramid. Now, why would we call it that? Well, because what we actually have are 2 pyramids, right? Each one with a triangle as the base. So there's the top of the one pyramid, here's the top of the other pyramid, and the 2 pyramids are actually sitting base to base. Okay, so it's 2 pyramids, each one with a triangle as its base. So that's where that particular name comes from. So that's the AX5 situation. So let's look at the AX6. Now, in the case of the AX6, we're going to do a similar kind of thing here. But now what I'm going to do is I'm going to add 1 more electron pair to the equator. Okay, so what I'm going to end up with is something that looks like this. right? So then I'm going to have essentially an X coming out like this. I'll have an X going back into the board, another one coming out like this, another one going back into the board like that. And then I'm going to have an axial X and an axial X. So again, we have equatorial X's and axial X's. And now if you look at the equatorial one, you look straight down on it, what have you got? You got a square now, okay? So you can actually see the square there. It's actually being generated. Okay? So I've got a square looking straight down, and then of course I've got my two axial electron pairs as well. So now if you look at this, looking straight down on a square, what's the bond angle looking straight down on a square? Well, that's 90 degrees, right? So again, on the equator, my bond angles are all equivalent at 90 degrees, but I can also look at my axial bond angles, and those are also going to equal to 90 degrees. Okay, so in the case of the AX6 situation, okay, all of my bond angles are the same, regardless of whether they're going to be axial or equatorial. All right? So we have a name for this. We could call it a square bipyramid if we wanted to. That would be acceptable, but we actually have a better name for it. We call it an octahedral geometry. That's an octahedral geometry. The reason we call it that is because if we applied actual faces to each one of these things, you would end up with 4 faces on the top, 4 faces on the bottom, so that would be a total of 8 faces on the polygon, so that's where the octahedral terminology comes from. All right, so these are the basic geometries, parent geometries that we're going to deal with. So when we come back and deal with this in class, we're going to look at specific examples based on Lewis structures, and then we're going to see that these also have subsets associated with them. Because what happens is we have to differentiate between bonding pairs of electrons on the central atom and non-bonding electron pairs on the central atom. So we're going to take a look at those different subsets as well. So this is where we're headed next time, so we'll see you then.